All right, so this is a video that goes with the skill of being able to map by rotating or reflecting a polygon onto itself. And when we're mapping something onto itself, what that means is that I want to be able to rotate it or reflect it so that the shape looks the exact same as it does when it started. Now, the most important part when you're thinking about rotating this figure is that we know that a full turn all the way around is 360 degrees. So if you have a regular polygon, if you want to be able to rotate that figure and have it look the same, what you need to do is you need to take 360 degrees and then divide by the number of sides. So this is a regular pentagon. A regular pentagon means that all the sides are the same length. And I'm going to take that 360 degrees and I'm going to divide it by 5. Now, when I take 360 degrees and divide it by 5, that's going to give me one number, and we're going to use that number multiple times. So when I take 360 and divide it by 5, that gives me 72 degrees. So that means that I can rotate this figure every 72 degrees. So if you think about this as our starting point, and we are rotating it clockwise, so rotating this way, if I rotated it 72 degrees, then it would look the same. And if I rotated it 72 more degrees, which would give us a total of 144 degrees, it would look the same. And if I take 144 and I add 72 degrees again, then it gets me to 216. And then 72 again gives me 288. And then a full 360 would obviously keep it looking like it is. So the minimum number of degrees needed to rotate it onto itself would just be that initial 72 degrees, okay? Because it's asking for the minimum. Obviously, if I rotated it 360 degrees, I'd end up in that place as well, but this question was asking about the minimum, okay? So number 2, instead of giving us the polygon and having us find the measurement, it's giving us a measurement and asking us to find the polygon. Well, we can just use that same equation, 360 divided by the number of sides. We just don't know what the number of sides is. So if I take 360 degrees, and I'm going to divide by some number of sides, but I don't know what it is. But I do know that the minimum measurement is 45. So just like in number 1, I knew I had 360 and I could divide by 5. I'm taking 360, but I don't know what I'm dividing by yet. So what I need to do is I need to get n by itself. So the first thing I'll do is I'll multiply both sides by n, because then my n's cancel. So now I have 360 degrees is equal to 45n. And so to find that minimum number of sides, I'm going to take 360 and divide by 45, and that gives me 8 sides. Or if you want to think about it another way, we could have just taken 360 and divided by 45, and that would have given us our number of sides. That number of sides is 8. That's an octagon. So that's our regular polygon. All right, in number 3, we have a square that's graphed in this coordinate plane, and we want to reflect it onto itself, and it gives us some options for some lines that will reflect it on itself. So a reflection over which line does not carry the square onto itself. And our first option is x equals 5. So let's see if I can make this bigger. There we go. So if I have the line 1, 2, 3, 4, 5, x equals 5 is that line. And so if I rotated over that line, it would flip over here. And now most of the square would be on this side of the line and a little bit of it would be on this side of the line. But I know if I'm going to reflect it over x equals 5, the shape isn't going to look the same. So unfortunately, they gave us the easy answer right away. And so the answer is going to be x equals 5, but I want to rotate some stuff around so you can see what's going on here. So if I wanted to rotate over x equals, or y equals 2, what I'm going to do is I'm going to go to that line y equals 2, which is right here. Now, y equals 2 is going to result, if I flipped this, then we would still have 1, 2, 3 squares on the bottom, 1, 2, 3 on top. Because y equals 2 is what we call a line of symmetry. Well, that's really nice. So anytime we have a line of symmetry, that means that I can flip the figure and it still ends up on itself. Let's take a look at these last two to see if they're lines of symmetry. So I'll erase that. I'll get rid of all this for now. So let's take a look at the line y equals x. Well, y equals x is a line with a slope of 1 that has a y-intercept at 0. So I'm at 0, and I'm going to be this line. And it would go down as well. Well, it looks like this is a line of symmetry as well. It crosses here, and it divides that square into two triangles. And so y equals x is a line of symmetry, which means that if I flipped this square over itself, it would look the exact same. All right, for the sake of not having enough time on this recording, we won't take a look at that last line, but it will be a line of symmetry. Okay? All right, let's go ahead and keep moving. Let's see if I can pinch this and make it a little smaller. Okay. All right. In number 4, what fraction of a turn does the model of a Ferris wheel need in order to appear the very same? How many degrees is it? Okay, so what we need to do is we need to think about this as a polygon with the number of seats as the number of sides. So there's 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is kind of like a polygon with 18 sides. So if I want to know what fraction of a turn needed, well, that fraction of a turn would be 1/18 of a turn. So every time I turn this 1/18, then there's going to be a seat that it's at the top and it's going to look the same it is right now. If I want to figure out how many degrees that is, that's just easy. We're just going to use that formula, 360, and divide by the number of sides, which is 18. That's going to tell us what fraction of a turn we would have. So 360 divided by 18, that's 20 degrees. So every 20 degrees, this Ferris wheel is going to look the same. All right, I'm going to do 5A and 5B just so you get the hang of things before this time runs out. So in number 5A, it says describe the rotations that carry the regular hexagon onto itself. Well, a hexagon means that this has 6 sides, so I have n equals 6. So if I want to find the rotation, then I know that this is going to work every 60 degrees. So this hexagon will look the same at 60 degrees, 120, 180, adding 60 more is 240, 300, and 360. So these are the rotations that'll carry that hexagon onto itself. Now if we're talking in number 5B about reflections, well, if I want to reflect this onto itself, that implies that everywhere I need a line of symmetry. And so this hexagon is going to have a line of symmetry in a vertical line and in a horizontal line. We're also going to have lines of symmetry if we cut this diagonally. And that's a terrible drawing, but hopefully you can see that if we reflected it over the line created by, is that EB? That would be a line of symmetry, as well as AD, as well as the vertical line and the horizontal line. All right, hopefully that helps you understand a little bit more about what's going on when we're trying to rotate or reflect a figure onto itself.